I'm currently at Cisco Systems, technical leader for IPv6. In my past life, I was program manager at Microsoft for IPv6, and before that I was the associate manager at the Energy Sciences Network for the U.S. Department of Energy. So I've been on your side of the thing in terms of operations, been probably the bane of some of your existence, building stacks at Microsoft, and now I'm trying to help life. So anyway, today we'll get in and talk about V6 and cover just fundamentals. How many of you have spent any time thinking about V6 at all? Okay, how many of you have actually read some substantial documentation and think you have a good clue as to what's going on? Enogen, your hand has to be higher than that. How many of you have actually written some of the documentation that everybody else is reading? Don't feel bad. I'm just trying to gauge, how bad the questions are going to be. Feel free to throw any questions out. I want to be interactive. I don't want this to be me preaching to you guys. I want you to understand what's going on when we get done here. So, jump in. And I'm not going to worry too much about hard questions because we're only 2 or 3 people, right? So, and Enogen doesn't get to ask any. So, and my machine's asleep. Oh, this is not a good time for this. Did this to me a couple weeks ago. Waits until you're standing in the middle of a presentation and then won't page. We'll give it a second to wake up. It's probably swapping somewhere. I've got VMware running with a FreeBSD VM in the background, and that's just enough memory that between PowerPoint and VMware it pushes it over the edge sometimes. Anyway, so V6 is more than just a different way to spell IP. Excuse me. For those who have spent some time thinking about it, how long a time frame are you thinking about before you actually are getting ready to deploy this? 6 months? A year? 2 years? 5 years?
8 to 5.
And the customers need it? Okay. I really don't know why that's doing that. See if we can get its attention by pulling the network out. Yeah, the answer to when you're going to need to do it is partially going to be when your customers demand it. Clearly that's what most people are going to be looking at is customer demand before they start doing something. This is one of those funny technologies where if you wait until the customer demands it, you may not be able to move fast enough, right? You may need to have just a little bit of a running head start before your customer demands it, because you may get run over if you aren't quite ready. This was working fine right before we started here.
We can just
switch slide decks.
Let me get it open and supposedly we should just be able to put that cable in here, right?
Yeah. For those who want to actually follow along, there are slides on the website, but we had some logistical problems between mail and me not knowing what was supposed to happen. So they're only in PowerPoint at the moment. We'll get the other formats available as soon as we can. But for right now, they're only in PowerPoint.
We're thinking that we may switch presentation format so that people would give us slides in PowerPoint, but the only thing that would be on the web would be PDF.
Get into some detail about where the differences are. There's the power right here. I'm not going to need it.
Okay.
Get into the technical differences between V4 and V6. I was describing this to some network managers a couple weeks ago, and I said, if you really think you know what's going on with V4, you're going to be really confused with V6. right? It's just close enough you think you know what's going on, but it really isn't the same. There are some enhanced capabilities. We'll talk about which ones of those are real, which ones of them are just publicity. There's quite a bit of inaccuracy and speculation floating around, particularly on the NANOG mail list. You know, I pulled some comments directly off the NANOG mail list and tried to answer those. So that's mine. We'll just get it out of the way. And then spend a little bit of time towards the end on transition technologies, more as an introduction. To do this course justice and get you enough detail that's actually useful, we ended up splitting it because, you know, it's like 3 hours worth of stuff. So we'll do an hour and a half at this NANOG, and then I'll do the other hour and a half at the next, where we'll go further into detail in the transition technologies, how they get deployed, what combinations make sense or don't. But we'll do a quick introduction to them here. So, why a new IP at all? You know, we've got IPv4, life is wonderful. You know, why should we be moving on? In '91, we started looking at the run rate for v4 address use and trying to project when we would run out. You know, it wasn't a question of if, it was just a question of when. So several different projections were done, and you can go back and look through the archives and you'll see they span from, you know, late 90s through 2025 or something like that. I mean, they're all over the map. There aren't any good, you know, hard data projections.
I'm confused here. Do you have a different, do you have a male and I have a female or something?
No, this one goes in there.
Thank you.
Okay, thank you for your laptop. I appreciate that.
Yeah.
Anyway, so, you know, the consensus was 2008-ish was, you know, the best we could come up with. So several different proposals were put together trying to figure out what's a reasonable technology to go forward with. We had a bake-off in '94, and what we know of as IPv6, to a rough approximation, was the winner of the bake-off. For those who actually wonder what, you know, happened to IPv5, that question comes up from time to time. Here's the actual assignments over time. You know, 6 through 9 were the evaluation versions for the possible choices for the next version of IP, and version 5 is in use in a few buildings that nobody knows. You know, they're gray buildings with locked doors. You can't see what's inside, but it was built, is being used a little bit, but certainly not by anybody in a production network that we see. Excuse me. At this point, 7 through 9 could be recaptured, but it hasn't been done. So do we really need more address space is another question. If you step back and you think about how many people are on the internet today and use it all the time, you know, a fair number of people have the address space they need, I mean, particularly in North America. Those that don't, most of the applications they're using work fine behind a net. So functionally, they have the address space they need. So do we really need more? Well, there's a whole series of stuff coming. The mobile phone community in particular has been pushing, they want to deploy 1 billion nodes at a crack, right? You know, take a quarter of the v4 space every time we go out and do this. They think, you know, there are 1 billion phones out there now, and they want to grow that number, and they want them always on the network, right? So that's a lot of addresses. You can't use DHCP and reclaim them because they're always on. And then, you know, consumer devices. In 2001, Sony put out a press release every month. And, you know, the sum of all of those press releases was every consumer device that Sony ships with electrons in it will be on the network. You know, think about how many devices Sony ships with electrons in it, and put in, you know, IP address on every one of those, always on. And that's going to chew up a lot of address space. So, you know, the only way they could foresee doing that was to put v6 in the box. So they're going to be putting a lot of V6 nodes out there in consumer land. When? Ask Sony, I don't know. But that's certainly, the direction they were announcing last year with a press release every month. So it's coming to a neighborhood near you, and it'll be disguised as a refrigerator or, who knows, right? But, the stuff is coming and in all kinds of forms. Oh, actually, while I was on that page up, where's the page up button on this laptop? There it is. The lower right-hand corner, I put this up one day, and the guy said, yeah, we were getting ready to put our fuel pumps on the internet. Right. So, that's not just marketing. There was actually a guy that was getting ready to do that. This slide could be a rat hole, and I don't want a rat hole here. You can talk to Aaron some more later this week about details on this. I just went off to the IANA website the other day and pulled down the what isn't allocated from the Aaron pool or from the IANA pool, the root pool, and put that as the endpoint on the graph. The detail of the graph comes from RFC's historical data, and then his name escapes me. A gentleman from Genuity actually sat down with the registries last year. Scott, yes, sat down with the registries and got some more granular data. So everything up to the last data point is based on either RFC's or Scott's data, and then the last data point is just off the free pool on the IANA website. Anyway, the reason I wanted to put this up was not so much to show projections. Late August, I was in Shanghai talking to the education network manager there. And during his talk, he said he could use 72/8s if he could get them. And, I thought, that's a nice big number. I wonder where that came from. So over dinner, we were talking, and he said, this is such a fun talk today. Later, go away. Anyway, he said he's got 320 million students, right? And that number just kind of sat there, okay, fine. Then I started thinking, 320 million, that's actually larger than the population of North America. I don't know exactly what the number is, but it's under 300 million somewhere. So how many /8s does Aaron manage for North America? I went and actually looked through and my back of the napkin calculation of the legacy /16s and say, oh, okay, about this percentage of them is probably Aaron. Comes out to about 75. Right, so you throw away a few odd ones like MIT and Apple and guys that are obvious consumers of a lot of space, you still are in the ballpark. 300 million takes about 70-ish /8s to support it. There's only 90 left. Right? Effectively, the party's over. If just the education network in China could get the space they need, there's no V4 space left. And that doesn't count the other 3/4 of China. That's just the education network. Right? So, yes, we need a lot of space. And V4 isn't going to work. Oh, also, while I was on that page, so anybody else who wonders about it, there's an RFC that Christian Wiedema has been working on for a while, 3194, talks about address allocation inefficiency when you've got hierarchy. Right? So you can only use a certain amount of the space even if, so you can't use all 4 billion addresses no matter what. So what were the goals of a new design as we started looking forward? Excuse me. We decided that, we had to be able to support always-on technologies. You can see that coming. In the early 90s, always-on was pretty much the common case. Mid-90s, dial-up started, the HCP came in and started reusing the address space on a fairly aggressive basis. So we were sharing space, but as we move back towards DSL in Tokyo, I've been hearing a lot of reports that for less than $100 a month, you can get Gig E to the home on fiber, right? So, this stuff is coming in various parts of the world. It is always on, and it does chew up a lot of address space as it does it. So we decided, 10 to the 15th endpoints is probably a reasonable goal, and 10 to the 12th sites to support those endpoints was a reasonable number. So taking all that and doing the appropriate math, 64-bit addresses are sufficient to support those two design points. And that was actually the proposal that was the V6 proposal in the bake-off. I was on the pragmatic side. The OSI address format was actually being deployed in real time at that point. And so I was saying, we should just take ownership and go with it, right? It's already there. We've already got it implemented in routers. Let's just use it. The primary reason that battle lost was because it was a flexible number of bits, and therefore routers would have a harder time dealing with it. But, some of the arguments about growth and scaling and the ease of address assignments stuck. And so we ended up doubling the V6 proposal and picking a 128-bit address that was fixed format. So you end up getting somewhat the best of both worlds. You've got plenty of address capacity to handle 10 to the 12th networks. You've got easy automation and a fixed format so the routers can move the bits in a hurry. And for anybody that wants to memorize this number at the bottom of the screen, that's a good party number to know, right? Every molecule known to mankind can have its own address. Again, apply Christian Wiedemann's discussion about address hierarchy, and you'll find that you'll never actually get all those addresses. But this is the new number that replaces 4 billion.
What would you call it? Would you say a billion?
It consumes an entire slide in 10-point font.
What would you call a reasonable number just to talk about? The same way you talk about 4 billion.
That's more challenging because I've got a different way of discussing that. And think whether this is the best place or not. Okay, this is probably the best place. One of the challenges with V6 is because we have locked in on provider aggregates as the primary allocation mechanism, multi-home sites cause the table to grow. Just same problem as V4, nothing new there. So what I was trying to do was come up with another mechanism for handling the multi-home sites. So I put together an address format that is based on lat long parameters. So, in 22 bits, I could allocate 64,000 subnets per 10 meter square. Right? So that's like 128 subnets per vertical meter for any reasonably tall building. So 128 subnets per vertical meter, half the size of this room, everywhere, including the oceans. That's a much easier number to deal with than whatever was printed there, right? And that's only 1/16 of the space. And so it's a much bigger number than that. Okay, we'll come back to that when we get to the address format here in a little bit. Japan has been pushing pretty hard. As I said, you can get GigE fiber to the home in Tokyo now. The Japanese government has had a tax incentive plan in place for a year and a half now or so, and a promotion council trying to get V6 out there. How many of you went to the IETF meeting in Yokohama? Did you see the taxis that were running around Yokohama with V6 enabled? One of the things they were doing was the weather station would like to be able to get much more fine-grained weather reporting than they can with their radar systems. So they outfitted the windshield wiper controls in the taxi cabs and were reporting back speed data on the windshield wiper controls, and so you could get very small pockets as all of the taxis in an area would have their windshield wipers on faster than other areas. So, you know, not only did you know it was raining in Yokohama, you knew which streets were actually getting pounded as opposed to just reasonable rain, right? But, you know, that's the kind of new application thinking that can happen when you don't have to worry about, you know, addressing every taxi cab windshield wiper control in the city, right? Addresses are free at this point. If you were trying to do that with V4, probably you could make it work, but that would chew up a big chunk of address space, and you'd have to go justify and, you know, why would you bother? So there's, you know, some things that are going to come out of the promotion council in terms of new applications that I think are going to be really innovative. They've been showing off the V6 refrigerator at a couple of shows lately. Not quite sure what it does because I've never been able to see one, but I've seen pictures of it. Korea is also pushing hard. I was in Seoul in July, and they were saying that 65% of the homes have broadband access now. Most of it's DSL, but you know, they're already past the point of just trying to get broadband pushed. They've got 65% of the population already behind a broadband connection, always on. The phone company was actually considering switching from traditional telephony to SIP-based voice over IP. Right? That's how much they're moving into this and how aggressive they're trying to be. China is trying to work on, you know, collaboration with Japan in several fronts. As I said, the education network can't get the address space they need. The rest of the country is trying to push into this space as well. So it's not just education. Excuse me. Europe is not as pressing in Europe. There are pockets where addresses have been more difficult to come by. So there's more of an interest in Europe than there is, say, in North America, but certainly not as urgent as it is in Asia. Did you want to comment, Adrian? Okay. One of the things we're trying to do is get back to the point where we've got an end-to-end architecture again. If you want to have your phone called as a destination endpoint on the network, it has to be addressable on the network, right? And you don't want 5 people sitting behind a net to have to go manually configure the net so they can receive phone calls. Right? This just has to work. Gaming is going to be a big push for V6 deployments. You know, peer-to-peer games where the current Linksys documentation is a 10-page book on how to configure the games that have already shipped. But every time you get a new game, you have to go download, you know, another couple of pages for how to configure for that game. And it's just, you know, on and on and on. You configure your NAT for V6 support once, and then the games just work, right? So peer-to-peer games, there's a lot of interest and a very low barrier to entry in that space. So what's different at a high level? You know, the addresses are 4 times as big. We'll talk a little bit more about it, but they also have scope. With V6, you get DHCP as an option, but you also have an option for serverless configuration. Now, this is a mode where the router is in charge of telling the nodes what address space to use. This avoids any potential for conflict between the routing infrastructure and the DHCP servers. Right? You know, you can't possibly get out of sync with the routers if the routers are the ones in charge. So that's one of the new capabilities. IPsec is built for V4 and for V6 as well. Primary reason it shows up is because it's mandated for V6 support. V4 it's an option. And if you're actually deploying in a NAT-based infrastructure, you have to go to extraordinary lengths to make IPsec work. You know, typically, it just doesn't. So it's, quotes, a V6 feature that you get IPsec because with V4, so much of the network is NATed already, you can't reliably get IPsec to run just anywhere you want to go. Mobility is another feature that's been described. Mobile V4 exists. Mobile v6 is slightly different. The primary difference is that it has the ability to get rid of the triangle routing, right? So with v4 mobility, you're forced into routing through a home agent when you're away from home. With v6 mobility, you route through the home agent to establish the connection, but then once that's established, you can tell the correspondent, oh, by the way, I'm over here now. Stop sending them through the home and direct shot to me. And it's, a lightweight tunnel is effectively what it is. So that capability is in there. We'll get into that a little bit more as we go down the road here. Quality of service. If you look at the press about all the wonderful things that v6 is going to bring you, it'll say quality of service. Reality is it's exactly the same. This service, this service, this serve. There's no difference. The one thing that v6 does have that v4 doesn't have is a set-aside set of bits for the flow label. Right? There's 20 bits set aside, and we're calling it a flow label. At this point, we're in the process of trying to define it. But until that thing is defined and the routers know what to do with it, you get no difference, right? So there's a hope that v6 will eventually be able to do something that v4 can't. But in the short term, quality of service is identical between the two. So what else have we got? IP multicast. Everybody's aware of IP multicast, I assume. The primary difference with v6 multicast is there are now 4 billion groups per subnet, right? So you don't have any of this managing group space problem anymore because you've got 4 billion of them on every subnet. It's the inverse problem. There are so many you can't figure out which ones are what. And the scoping for the range that those addresses are used over is defined architecturally. In v4, it's just kind of an administrative agreement what the scopes are going to be. But with v6, it's actually architecturally defined what the scopes are going to be. So, so when you get to the bottom line, v6 expands the address space to a very large number. We've got a lot of hierarchy and structure, expecting to grow the routing table in a manageable way. We've moved into the space where nodes can be more easily configured than they can with v4 DHCP. This is important if you're going to have a very large number of nodes beyond what you currently think of as a large number of nodes today. Your manageability only scales so far with the server. We streamlined the header format, which I'll show you in a minute, and then fixed extensions and options. Are there any questions before I move on from this kind of marketing stuff? So, okay, there's some advanced features. We'll come to those later, and don't want to spend too much time here. Okay, for just a general question, how many of you already have v6 allocation? A few. How many of you are thinking about you're going to do it? A few more? Okay. This page has the places that you go to find out what the current policy is. It changed in June, so hopefully the current policy is something that you can live with. When anybody goes at this point and signs up to get some v6 address space, you'll get a /32, unless you need it like now, and then you get a 35. But logically, everybody gets a 32. The expectation is that all sites get /48s. I'll show this again in a minute. That is, unless you're doing a single subnet, in which case, a /64 is okay to go ahead and allocate. /128s, there's a lot of debate back and forth as to whether you use those on point-to-point links on routers. You can, but it's kind of like a lot of pain to go through for not very much gain. So we'll show that here in a minute too. If you were in Asia, and I asked that question, there wouldn't be 6 hands, there would be 80 hands, right? There's a very large number of networks that have already gotten address space from APNIC. Europe is actually a bigger number. This was trailing behind until the last 3 months, and then they shot ahead for some reason. So, as of September, there are 90-something allocated out of Europe, and then North America. Right? It's like nobody in this community is really considering V6 seriously because they haven't gone off to get address space. Right? This is a very obvious statistic that you can look at and figure out where the interest is in various parts of the world and why there's a lot more customer demand in other places than there are here. Right? So we have a new header. We did this drawing and the graphics artist got a hold of it and screwed it up, and I tried to fix it and it doesn't look right. Anyway, the addresses are 4 times as big, but the header's only twice as big, so that's what I'm trying to show here. Several of the fields, those in red, are gone. They're either in extension headers or things like the checksum where nobody actually used it anymore. Right? It's just extra bits, so those are just taken out. The base V6 header, its whole function in life is to get the packets across the routing fabric as quickly as possible. If there's a function that doesn't have to do with getting the packet across the routing fabric, it's in an extension header. Primarily, those are in-system kinds of things to worry about. Right? The one exception is the extension header for hop-by-hop options, but for the normal case, you want to get those packets across the routing fabric. It's a fixed format, minimum number of fields to worry about. Just get it out there and go. Right? Everything else has been moved into extension headers. So, we streamlined it. We moved some fields out. Checksum's gone. If you really want a checksum, you can use the authentication header. It provides a much better integrity check of the header than just a checksum anyway. The link field now excludes the V6 header. The alignment has changed from 32-bit to 64 bits. Things to make it easier for you to process while you're at all of these changes. Interesting translation between my PowerPoint and yours. The time to live, the name was changed to protect the guilty. It's now hop limit, which is what everybody always treats it as anyway. Long ago, it actually did have to do with time because packets took more than a second to leave the box. But the protocol field is now called the next header field. Part of that is just recognition that what may be there is not just a new protocol, but an extension header or who knows what. But it's just the next header, whatever the header may be. Redefined precedence and TOS into traffic class, which it kind of was anyway, but for V6 there's nothing except traffic class. And then we added the flow label field, and if we can ever agree on what that thing means, you might be able to make some use of it somewhere. The fragment header. I put this one in here in particular. Routers do not fragment packets. Right? In V4, you end up with all kinds of weird cases because the routers might fragment, and then you have to keep track of all the fragments and put them all back together in various places. In V6, the routers don't do that. Path MTU must work. Either that or the host must send minimum size packets. Right? So one of the things that network managers have to do is go back and figure out, am I filtering ICMP messages that are blocking path MTU? If so, that's got to get fixed. Right? With V6, there was a little bit of help because it was given its own packet type. right? So it's got its own ICMP type just for PathMTU, so it makes it easier. You just don't block all ICMP, block the things you care about blocking and leave PathMTU open because you need that one to work, right? If a link can't support the 1280 byte minimum MTU for v6, it's all right for the router to fragment and reassembly, do fragmentation and reassembly across that, like ATM kinds of links, right? You're chopping the thing up and you put it back together on the other end. But it doesn't leave those two endpoints fragmented, right? So as packets are moving through the network from any point along the way, fragmentation is done by the end systems only, not by the network itself. I said we'd get back to address allocations. The registries had been allocated /23s. The old policy was networks would get /35s, but that's changed to 32s. So if you've got a 35, my understanding is you can go ask and they'll change it to a 32. So you don't have to go through the whole process again. There's only one semi-hard boundary in v6. And it's not like really hard, but for most formats of the address, the low order 64 bits are the interface identifier. The upper 64 bits are the subnet identifier, essentially what the routing fabric uses to get the bits to the last wire. As I said earlier, there's this expectation that sites will get /48s. Steve Deering did a study last year because there was some concern about possibly running out of /48s. And the 2001 format identifier we're allocating out of right now is 1/8 of the total v6 space. And according to the calculations he did for the population of the Earth in 2050, right, so 48 years from now, projected population, there are enough /48 in this one prefix for everybody to have a half a dozen personally, right? So we're not going to run out of these anytime soon. And with your /48, you now have 16 bits of subnet space. Anybody quick know what a correlation between 16 bits of subnet space is and a v4 allocation? More. 16 bits of subnet space. Right? Most people with a /8 have functionally 16 bits of subnet space. Right? You can play that, but it's on that order, right? So you're talking about every site gets that. Right? Plenty of space to work with. You're not going to run out anytime soon, and what you're managing at that point is subnets. The interface identifier, I didn't actually put any slides in on that. That's bad. So I'll talk. No, I guess I did. We'll come back to the interface identifier, and then what else is on here? Okay, this one's out of order. Format for how you actually type them in textually. Everybody who's used to dotted decimal, you're going to have to relearn. Right, it's colon delimited hex, very long strings. If there are long strings of zeros, like you've got here in this section, they can be compressed out with a double colon. You can do that once, right? So you can compress out and say, some number of bits, colon, some other number of bits. And because you can only do that once, you can back calculate how many zeros there must have been. It's a complete set of zeros. So if this had actually ended as FF00, it wouldn't be the 2 zeros with the Fs, it's everything between the colons, because you have to be able to count integer number of 16-bit zeros. There is some dotted decimal left, just to confuse things. There's a set of addresses that were used for coexistence with v4 and transition, and so they've got v4 embedded in them, and therefore to represent those and make it easier for you to figure out what's going on, we actually put the v4 part of the address in dotted decimal format, so you can say, okay, with this v6 prefix, I've got this v4 address that I'm used to, and this is being, for mapped purposes, this is something that an origin node would look at and say, that guy only speaks v4, right? That's what that particular address means. Right? I've got a v6 address that I got back, and so I'm a v6 node, and I'm aware of what's going on, but the guy I'm trying to talk to is a v4 only node. That's what the mapped addresses are for. There's another format called compatible, which is intended for automatic tunneling. Looks very much the same, except there's no F's in the middle there. It was a great idea, allows end-to-end tunneling because you've got the v4 addresses buried in there. But the only way you can make it scale is to inject the entire v4 BGP table into the v6 BGP table. So we're going, no, let's not do that, guys. It's probably a bad idea, right? So we're trying to discourage the use of compatible addresses. They're still in the documentation, but it's one of those we're trying hard not to give people a reason to use them. As I said, addresses have scope. So what does that mean to you? How many of you have seen a host auto-configured to 169.254 something? Link scope. None of your routers will pass those packets, right? Those are after the fact allocated for link use. 1918 addresses, everybody's very familiar with. Those are for use within a site. You guys don't route them between sites, right? So architecturally, we looked at what was going on and said, we've got fundamental use for link scope things. We've got fundamental use for site scope things. We should just architecturally define some space for those uses, right? So there are two chunks of address space set aside for link and site, and then the rest of it set aside for global. The primary difference that you'll see between v4 and v6 in this space is that in v4, it's possible for you to actually go configure a node to have multiple addresses, but you really have to work at it. Almost always they have a single address. In v6, they will have multiple addresses. Right? The only time you end up with a single address is if you're on an isolated wire with one other node and you're both using link local. Otherwise, you will have at least site local or link local and some other format, maybe site or maybe global. But you will simultaneously have multiple addresses, and they will probably be simultaneous addresses from multiple scopes. And this is where it's going to be a little more challenging in terms of figuring out exactly what's going on. Right? So if two nodes are on the same wire and they're talking to each other, according to sending rules, they use link local scope to talk to each other. Because it's the logical thing to do. If the router goes down, they don't care. They're talking to each other on the same wire. Right? At any rate, there are multiple scopes. They are used simultaneously, which is a big difference. And addresses have lifetime. Right? In v4, pretty much everything was there. You might have some lifetimes in DHCP, but that's really for you to come back to DHCP to get a new allocation. That's not any indication about the validity of using that address. It's more of, I'm supposed to go back to the server. With v6, the routers will announce on the wire, these prefixes are valid for this length of time. Right? The design for this is set up so that you can move a site from one provider to another in a graceful manner. Right? So you've got a week-long valid prefix lifetime for the old provider. You get ready to bring in the new provider. fine. You start announcing the new provider prefix. You can have multiples. It's not a problem. Right? So we're going to allow all nodes to have multiples. But I shorten the lifetime on the older prefix to 6 days and start shortening it every day, right? Well, the nodes that are aware of that prefix can continue to use it because it's still valid. But when they go to establish a new connection, they're going to use the longest available lifetime. Right? So the new provider's prefixes are going to have a longer lifetime. They're going to start new connections on the new provider's address space. Any existing connections can persist on the old one until your lifetime expires. If you've given it enough time, a few days is usually reasonable. The number of connections that you actually tear down at the end of that window is going to be close to 0, right? Because they will all naturally die off and new connections will all naturally open on the new service. So you don't do this hard cutover from one service provider to another as you have to do in v4. So, lifetime is there. There's preferred lifetime and valid lifetimes, just to make it more challenging. Give you enough knobs that you can actually do what you want to do from this. So I said a node will have multiple addresses. Here's the set, right? You start off, every node has a loopback address, and they have more than one. It's just doing weird things. Every interface will have a link local address. You may have site local addresses for use, and we'll talk a little bit more about those in a minute. For use within a site. We've got some transition mechanisms, 6 to 4 we'll talk about later, but that's an auto-configured type of address. There's auto-configured v4 compatible. We've got solicited node multicast. As I was saying earlier, if you think you know what's going on, you're going to be completely confused. With v4, there is a distinct address resolution type for every media you've got, right? So there's ARP for Ethernet, and there are other flavors of ARP for whatever variety of media you might be attaching to. With v6, there's one thing. It's called neighbor discovery. It's an IP multicast function. Right? So every node will come up and subscribe to what's called a solicited node multicast address, which is a derivative of its address space, but in the multicast space. And there may be collisions, but the number of collisions is low, and so the number of nodes that could possibly respond to this is, can be counted on one hand, and they're aware of what's going on, so you don't end up with massive problems here. There's an all nodes multicast address. We'll talk some more about anonymous, but there's global anonymous addresses, and then there's global published addresses. As I said, you could have multiple providers and you could do this transition. Well, you don't have to do a transition. You can actually have nodes with multiple providers permanently on. So like the Cisco campus in San Jose has 4 service providers connected full time. If we use this mechanism, you've got 4 prefixes in the global published and 4 in the global anonymous for every node, right? So I've gotten up to order 15 addresses per node in a hurry, right? So, with v4 you had an address. With v6 you might have a handful of addresses or a boatload of addresses, depending on your service provider characteristics, right? And there are rules for how you sort through these, right? Because if you've got a boatload of addresses, figuring out which one you're supposed to use is another challenge. I'm not going to spend a lot of time on these rules, but basically there are preferences given, and there are certain cases where it is actually smarter to use the v4 address. The most obvious is if the 2 nodes have global v4 addresses, but they have mismatched scopes of v6 addresses, so you pick the thing you know is going to work, the global v4 addresses, right? So follow through the rules. You pick your source address and your destination address, right? Because you've gone off to DNS and you've gotten back this list for the other guy. right? So you've got a list for him and a list for you, and you got to go, which set of this, right? It's longest match, as the default tiebreaker here, right? So the intent of that was that if you're sharing a service provider, since we're doing service provider-based allocations, if you're sharing a service provider, you probably want to pick the address pair that actually uses that shared service provider, because the service will probably be better than if you're going through some number of exchange points somewhere or peering points, right? So, the goal is to make things work as well as possible without a lot of manual effort. And if you don't like the rules, you can always override them with local policy, right? Since this is an in-system function, local policy on the box can say, I don't care what those rules are, you're going to use this set of addresses, period. Right? So you can override this. So the various formats. For link local, there's 10 bits set aside that identifies, okay, this is going to be a link local. The next 54 bits must be 0. And then the low order bits are the interface identifier. And to make the configuration easy, we're saying take your MAC address and jam it in there. There's an algorithm for how you take a 48-bit MAC and jam it in there. When IEEE starts allocating 64-bit MACs, they just go straight in, right? For use on the wire, that's the simple thing to do. You don't end up with any collisions. You can double check and make sure you're not going to have collisions, but that's what that's all about. For site local, we've got another 10-bit identifier set aside for that. The original specification tried to align the subnet administration with the global space so that if you're administering a set of subnets for use within a site, you want that particular set of bits probably to match the service provider things that are coming in, right? So we said, 16 bits, and there were enough people complaining that they actually wanted to be able to use this mechanism between sites for their internal private network. We went ahead and opened it up, so all 54 bits are for local administration. But the smart thing to do is keep that 16 bits in the middle the same between your global space and your private space, and make it much easier for you to find the subnet you're looking for. Right now, the number of subnets you manage is a fairly small number in most cases, unless you're MIT or HP or somebody that's got a big chunk of address space. The interface identifier can be MAC derived again. It can also be administered through DHCP or manual static configuration, whatever you want. There's not a lot of structure to that other than if you're jamming in the MACs. So the global one, registries are allocating to service providers are allocating /48s to sites. So then you've got 16 bits of subnets for local administration within the site. The interface identifier can be the MAC again, can be locally administered, and it can also be a random value. And I said we could have these privacy addresses. I don't think that's what I call them. At any rate, what they're for is to avoid the problem of being trackable. In the case here where I'm using MAC addresses, if I wander from service provider to service provider, I'm at Starbucks in San Jose, I'm at Starbucks in LA, and I'm at Starbucks in Seattle, bang, 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 and they know I do this track every week, right? When I start showing up, there will be an ad on my laptop telling me about something, the place next door, because it knows I'm going to be there, right? I'm trackable if I'm using my MAC address. It doesn't matter which service provider I'm on, that MAC address constantly shows up. So with the problems that Intel was having with CPU serial numbers and Microsoft was having with GUIDs, it's like, no, you don't do anything that's trackable to that granularity. So we put random numbers in here. For services that you expect for somebody to call you, like you're pretending to be a server, your phone, you're a game host, whatever, you're going to register something in DNS, therefore you're not anonymous in any case. So you might as well register your MAC address. You're you're trackable through DNS, therefore you're trackable, therefore it doesn't matter what you use. So we're recommending you use the MAC-based addresses for DNS. But for anything where you connect out and establish a new connection, you want to use the anonymous values. That way you're not trackable, right? Current policy of all the implementations I've seen is they roll this number once a day. So you use it for a day and then you use the new one for the next day. The truly paranoid will roll this once a connection, right? I don't want any connection tracked, period. And so, you know, every new connection gets a new random value. Think about what that does to your neighbor cache, your functional equivalent of the ARP cache, right? If somebody's rolling one of those every connection, they could blow out your cache in a hurry, right? So you want to discourage the paranoid, but you know the service is there. There are several tunneling formats. Compatible address, we just jammed the low order 32 bits with the v4 address so you can find it and tunnel. Again, that doesn't scale too well. So what we did is we took and put the v4 address up in the prefix space as if it were a service provider allocating this. Right? So now I get all of the same capabilities that I have with a v4 or with a v6 global address format, because I've got a /48 allocated to a site, but it's derived from a single v4 address. Right? So any global v4 address, I can jam one of those in there, and now I have an entire 80 bits for use by the local site. I don't need to do neighbor discovery across the v4 cloud because I already know the destination address for the next lower down layer. It's embedded. Right? So I just yank out the v4 address, slap a v4 header on, ship it. The guy on the other end takes the v4 header off and knows where to deliver v6. Does the same thing coming back. Right? So that's a fairly straightforward one. ISOTAP is a new thing that hasn't actually gotten all the way to RFC yet, but it's architecturally the same thing, but putting the v4 address back down in the lower 32 bits again, while allowing for the upper part to be actual prefixes instead of all zeros, right? So you can use 6 to 4 and ISOTAP together where you tunnel within the site so you don't have to actually upgrade all the routers within the site to v6. You get to the edge of the network and then you can tunnel again using 6 to 4 across the service provider network until they all get to where they can support it. Did you want to do? We're going to change tapes, so it's going to take a second. In this particular case, where you take the network prefix, there it is, the 64-bit prefix for this subnet is embedded in here as well. So I can now have 4 billion groups per subnet, right? And administer them locally within the subnet. So I don't have to worry about all this sharing and other nonsense that's going on. There's a lot of work yet to be done in this space, but the address space is set aside and certainly can handle growth for as long as we're going to have to worry about it. Routing, something you guys probably all care about. Exactly the same, like just more bits. There are distinct RFCs that tell you exactly what's going on, what changes were made. Probably the biggest issue for anybody running OSPF is, OSPF version 2 for v4 and OSPF version 3 for v6, and so you're going to have a little bit of a learning curve challenge to run them both simultaneously for a little while till something else happens. Anybody that's running ISIS, that's address family was already designed to handle a large address family, so it was a fairly straightforward drop-in, right? So ISIS networks don't see too much change. Okay, security. All implementations are required to support IPsec. This is required in quotes. No, it's not in quotes. Should be. The requirement is there. Not any implementation that I'm aware of supports all of IPsec yet. Right? So they're all still in the process of catching up with this particular requirement. But in the grand scheme of things, in a year or two, all nodes will support IPsec. Key distribution is not any better than it is in v4, right? So that's still going to be the blocker. The nodes can support it, but unless you've got a key distribution infrastructure under you, it doesn't really help. Quality of service. As I said earlier, they're exactly the same. Diff serve is diff serve, int serve is int serve. They work the same way. They're just moving bigger headers around. I don't think there's anything really to say here. Okay, the 20-bit flow label. It's possible that we can figure out some mechanism for RSVP to signal what's going to happen and land in the flow label. It's also possible that the end nodes just use some heuristics for how they allocate these based on local site policy. As the flow label spec is written, there is no structure or clear mechanism for how that 20 bits gets defined. Right? So even if we get to the point of agreeing that it gets delivered end to end without being modified in the network, there's still no clear definition of what that bit pattern means and what you're supposed to do with it. So that's work in progress. Signal diff serve is a nice compromise between the two. Mobility, I said we'd get to that. Mobile hosts can have, yet another address. And I said you've got all of these wonderful addresses per interface. If you're mobile, you've got a home address. The thing that you're known by when you're home. There's actually a set of addresses, but we won't go there. We'll just say you've got one for the moment. You've got this home address. Somebody tries to contact you. The home agent router says, oh, that guy's not actually here right now because I remember he told me he was over there, and we'll tunnel the packets to you. Right? So the packets come directly to where you're at right now because you've told the home agent when you show up somewhere else. When you receive those packets, then you tell the correspondent node, I'm over here, and what it does is wraps the home agent, or the home address is an option, and the outer address is your current care of address. So it still goes across the network as fast as possible because it's just an address that gets you to an endpoint, right? When you receive it, you recognize that it's got an option for a home address, so you rip that off, and that's what you're actually using to maintain the application connection, is the home address. With that, you can wander between networks, and the application doesn't perceive that the address is changing out from under it. So, ICMP we talked a little bit about. It's basically the same. There are parameter messages that are distinct. There are packet too big, I said, was an explicit message type. That was to allow us to be able to get it past filters or get filters rebuilt so that it can be allowed through without having to worry about some of these other choices. There are some neighbor discovery functions. In particular, you want to know who your routers are on this link. The routers will come up and announce their presence and say, I'm a router. And here are the prefixes for use on this wire. That's an ICMP message. The end nodes can take those messages and auto-configure themselves. If they do that and they choose to register those back in DNS, you have to think about how you're going to do a dynamic update for DNS, right? If the node is wanting to do that, and it's the only one that knows the address because it just generated it, right? So there's a tie here between the mechanism for auto-configuring hosts and an infrastructure that supports dynamic updates. You don't have to go down that path, but that's one of the consequences of doing it. If you don't, you end up with the same mechanisms you have today with DHCP, allocating the address and managing the DNS updates. Excuse me. You know, I'm going a little bit quick here because we're running longer than I expected. Okay, when the router talks about, you know, sends out its announcements, it'll send out the, you know, I'm a router, what the lifetimes of the prefixes are. It'll tell the nodes whether or not they're supposed to use DHCP, right? And whether that DHCP is just for addresses or for things other than addresses. So you can tell the nodes through the router advertisement, here's a set of prefixes, and we're managing address space from the routers, but we're managing all this other stuff, which is site local policy kinds of things, through DHCP. You can tell the, you know, nodes what the link MTU is. It's assumed to be 1280 unless otherwise specified larger. 1280 is the minimum link MTU. Right, so it's considerably larger than it was for V4. We made it 1280 to allow for the fact that if you had IPsec and mobility running at the same time, when you got all those extra headers and a V4 transition mechanism, so you've got all these headers chained, you might not be able to fit it in 1500 bytes, right? So we backed it down to where it would, you could put all these extra headers on it and still fit it in 1500 bytes. Okay, so nodes can find each other through multicast. They, you know, send solicitations and advertisements back and forth. And, you know, there's a flag in there so you can tell whether the node is a router or not. And the first question is going to be, are these things secured? And the answer is no. Right? It has the same security as ARP. It's just there. Right? So there's a little bit of a hole that's being looked at right now for how to secure this, because anybody can come up and claim to be a router. And you probably don't want that. Hosts, in the general case, hosts are expected to use this router advertisement to configure their addresses. It's expected, you know, as we were putting this together and looking at the number of nodes, you know, DHCP management becomes a real problem when you start to grow it, right? So the only way to scale the number of nodes up that we're talking about is to get past DHCP. So we're trying to make this the normal case that nodes self-configure. And they're also expected, because of this privacy issue, to be using these temporary addresses for outbound connections. If you really, really want explicit control, you can do that. One of the things that we're in the process of trying to figure out right now is what happens in the case where a node is self-configuring off the router advertisement, but there's no, you know, DHCP option that says, oh, by the way, DNS is over here, right? And see, how do you find DNS if you're doing self-configuration? We've got a couple of mechanisms written up. There's some arguments going back and forth as to which to pick right now. My personal preference is a link local multicast, but that doesn't seem to be winning the day. There's, you know, a strong preference for a defined anycast, which is a routing advertisement, host route functionally into this space. So you've got some well-known addresses that you go to. At any rate, whichever way it comes out, there will be a mechanism for nodes to find DNS. You know, address and DNS are the two fundamental things. Once you've got that, you can pretty well go from there. But if you don't have DNS, you're kind of stuck. We already talked about how to do the renumbering on the fly. There is a router renumbering protocol that has been defined. So you can sit at one point in your network and propagate prefixes out to all of the rest of the routers. So you don't have to go touch every router to tell it a new set of prefixes to use. Haven't seen a lot of people really excited about that yet, but it is defined in there if you care. Again, MTU is 1280, and you know, routers are not going to do fragmentation. As you can see, we seriously grew the number of bytes from 68 to 1280. It would have gone larger. In fact, the guys that are working in the 10 gig protocol space say 64 kilobyte frames is not big enough, because if you get any latency, they just can't keep it full, right? So it's coming. It's going to be bigger soon. If PathMTU is not working for whatever reason, nodes can send 1280 byte packets and expect them to be delivered. Right? So all links must be able to support that. Quickly to get into some of the speculation. In fact, I just saw mail last night that we're not running out of v4 addresses because we're not handing them out, right? Yeah, if you can't get one, we must be out, right? The only people asking about v6 are the people who've heard something about it, and therefore they just want to know. Well, in North America that's probably true, but in Asia it's definitely not, right? They're pushing hard in that space because they have a real need. The Japanese government didn't put out a tax incentive to get people to move because they thought this was a cool idea. They want their economy to move into a new space. They want to be able to do new things that they just can't do without address space, and they can't get it. So they're looking at this as strategic, economic, push. IPv6 adds node functionality over v4 with NAT. Well, if I'm running mail or web services where I'm a client, this is true, right? If I want to put up a web server, this is not true, right? Another classic example, my son just wanted to put up NFS between his two Linux machines. He's got two Linux machines in his room, but they're on opposite sides of the NAT that is feeding the house. And of course, NFS won't run through that, and RPC won't go. So, I said we can put it on v6. Well, that's fine. We got v6 running between his two nodes through the 6-to-4 router in the NAT, but there's no NFS for v6 on Linux yet. I tried to convince him to switch to FreeBSD, but he wouldn't do it.
Microsoft Active Directory doesn't work if you have multiple routing. It only works in a single routing.
It doesn't work in the current routing domain, single routing domain, or it only works in a single routing domain in its current implementation. I don't know that it's going to work in multiple routing domains, but I know it's. Yeah, it's also true that they're pushing very hard in this space, right? It's a very large army of people was working on workarounds for NATs, right? And so the question is, do you pay this army of people to work around NATs, or do you pay them to fix it so that people don't have to work around NATs? There's some motivation that is just business self-interest in that space. Okay, peer-to-peer applications, like I said, games, it just doesn't work, right? If all of the participants are not in the same address space, they can't share information with each other directly. You can do it through a central server that's on the public space, but they can't do direct peer-to-peer and get it to come out right. That was short. I've got another couple of slides, and I don't know why they're not showing up here. v6 deployments will come from the edge. As we heard earlier, people are going to wait till they hear their customers demand it. Okay, well, so fine. Customers are at the edge. So until they start demanding it, you're not going to do a lot of work in the middle, right? What you need to be looking for are protocol type 41 packets. Right? If you see a lot of protocol type 41 packets flying in your network, that means your customers are, quotes, demanding v6. They're not actually telling you, they're just using it, right? And they're using v6 whether you're ready or not. And they're just tunneling over your v4. So that's what's going on there. Another comment was the v6 routing would change drastically. Not really. Routing is the same. There are some concerns and issues about the potential for growth in multi-homing, but outside of that, there's not anything that's really different. One of the things that I keep trying to bring back to the table is that there are only 11,000 ASs injecting routes into the v4 table. If you go to this space and you do a dynamic reclamation of all of the prefixes that people are announcing, so that you give them all, everybody but HP has, at most 1/8, right? So they all get 1/38. There's only 11,000 entries in the entire system, right? And so you got some service providers doing traffic engineering. Double it. I don't care. And it's not going to be that big a deal. And that's even if you just inject all those prefixes in there. It can be a lot better. So routing is not as big a problem as people make it out to be. Multicast has its own set of problems to get worked out, but whenever it gets worked out for v4, we've got more than enough extra things for v6 to make it better. Interface IDs have privacy issues. This one comes up from time to time. As I said, the original definition, you take your MAC address and jam it in there, that does have privacy issues, right? But by using these random values, we get around that. You can use DHCP, you can manually configure, there's all kinds of options. Privacy addresses, or the interface IDs are not a privacy issue. They can be if you choose to let them be, but they are not by definition. There's been a complaint that the privacy addresses actually cause an infrastructure impact on DNS. And yes, if I chose to register the privacy address in DNS, I could churn DNS, especially if I'm doing it once a connection. That'd really be silly. And every time I open a new connection, I go churn DNS. But it makes no sense to do that, right? I shouldn't be using something that's designed for privacy with something that's explicitly not private. Right? DNS is not private by definition, so why am I using a privacy function? So you could, but nobody's going to actually do that. I put together this timeline to try to put this in perspective. There was a lot of grief in the press, especially middle of last year, saying, oh, v6 hasn't happened already, therefore it must be dead. Right? Well, it's a project that takes a long time. And in fact, there's a sequence of things that have to happen before it can really be deployed. You've got to have applications. If you don't have any applications, what's the point? We can have the best network in the world, we can have the best in-system stacks in the world, but if the application is still calling the v4 API, it's going to ship v4 bits. Until the applications get ported and start calling the v6 APIs, you're not going to go anywhere. Service providers, to a large degree, they're going to wait until they see applications come to the market, right? They see that there's going to be demand. Some of them will wait around until they actually hear the customer call, but some of them will be looking and they'll say, oh, there's applications, somebody's going to call, I'll step in front of it, right? But either way, that isn't going to happen until after applications get on the move. Consumers, if we've exposed which version of the protocol that is running to the consumer, we've really screwed up, right? Consumers type names, they click on links, magic happens. If they know that it was v4 or v6, it's just screwed up, right? So some holiday purchase they make somewhere along the way here, they're going to get v6 apps in their PlayStation or their whatever, right? And it's just going to go. Now, the early adopter kind of guys that have to go reconfigure the net may be aware, but the general consumer shouldn't know. Enterprises, on the other hand, think they have people that know what's going on. Right? They've got this entire staff of people that's trained in v4, an entire network management structure to keep this network running. They have to retrain everybody. They have to retool the management system. So even if they start at the same time as the consumer, they're going to be 6 months, a year later, just to go through the process, to get everything dealt with. Then you take and overlay that with the address allocation pressures in various parts of the world, and you get this thing skewing all over the place, right? So, if you're in Asia, you're on the leading part of this curve, right? Applications are coming out now, service providers are coming out now, consumers probably this holiday season will get a lot of v6 capable things. enterprises, sometime next year. If you're in the Americas, you're way out here, right? Because you've got enough v4 address space. Why are you pressured to move? APNIC has been telling people 2.5 years, go away. Wright's been telling them for 2 years, go away. Aaron's just now starting to tell people to go away, right? So, the pressure has been definitely in other parts of the world to get moved over. At the same time, remember back to that graph I put up before? Somewhere along the right-hand end of this, there's a feedback loop. Okay? This thing tails out because it takes a long time. Stuff people buy today is going to be 4 or 5 years before they get rid of it and buy something new, and they're not going to upgrade it. Right? So v4 only things that sell right now are going to stay there for another 4 or 5 years. But towards the end of this, v4 is functionally over. You can't get any v4 address space, therefore it's useless. So you've got to be moving into v6. There's a lot of skew, and if you're in Asia, you're moving quicker. If you're in the Americas, you're going to get there someday. But you can't wait forever because you're going to run out of v4 address space somewhere along the way here. And Aaron may have a better projection for that later in the week. Yes?
Several router manufacturers seem to have a problem with that, and then combined with deck-like pricing arrogance makes larger space on the floor to first have enough access to eco.
Okay, the question
How much space do you need for V6? And I'm assuming it's a lot more than how much.
the addresses are 128 bits instead of 32 bits. So a full... Well, the question, just to repeat since you didn't have the mic yet, was, the router manufacturers seem to be charging a lot to support v6, and therefore what is it realistically required to make v6 work in a router as opposed to v4? And there's several parts to that question, right? The simple, straightforward, fast lookup answer is I got four times as many bits to look at in the fast path. So, yeah, that's going to be more expensive. Okay. Another part of your question was how many megs in the router. Well, that gets back to the routing table size, right? And do I really need a 120,000 entry table for the prefixes in v6? And my guess is no. Right? It really depends on how people end up announcing and how much, quotes, traffic engineering they're doing by punching holes. But, if we end up with more than 15,000 entries in this table in the next 3 years, I'll be really amazed. Right? So how many megs does that take? I don't know. I don't get close enough to the hardware to be able to figure that out. But ask the router manufacturer what that would look like in terms of if they used a realistic number instead of 150,000 entries. So there's multiple parts to that question, and clearly handling 4 times as many bits in a hurry is more expensive. Yes. Inside Cisco, our hardware guys come to me and complain about that. I said, that's life. Get over it. Right. And, the world is moving on, so your choice is to handle that many bits or not. It's not a matter of, well, it's more expensive than v4, so we should stay on v4. And no, you can't stay on v4. That's not a choice. Right? Now, does that translate back into more expense to you? Unfortunately, yes. But it shouldn't be an outrageous expense. Right? And, that's me with my IETF hat on, to be very clear. Okay, we got multiple transition techniques. We'll talk more about these next time. The primary technique is dual stack. First question I usually get from people when they start thinking about v6 is, well, where do I need to put the translators? Right, because I got to speak between v4 and v6, and my answer is you don't do that unless you really, 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 really have to. Right? The only time you need to have a translator is if you've got a v6 only device that needs to talk to a v4 only device, right? And there aren't any v6 only devices yet. In fact, there aren't any on the drawing boards. There were a few. The 3G community was going to build V6 only handsets. They realized what a big mess this was and they backed off, right? So address translators shouldn't be required. We've got them defined, pretty much everybody has them built, but you shouldn't be deploying them as the standard mechanism. Dual stack is the basic mechanism you should be looking at, and tunneling in the places where you can't deploy V6 in a hurry. Yes?
Well, this is more from the customer-centric view rather than owner-centric, but that's my problem because I have to face it. Where we have private networks that use application-level cable. Jim Cutler, DDS. Looking at it more from the end network view rather than the North American network view, if you will. We have a private network that uses application-level gateways today for access to internet, for example. That's effectively a translation technique from what it achieves.
Right.
So that gives us an opportunity to change the private networks that might be on the order of a couple 100,000 systems total.
Well, in fact, you can take it a step further because you only have to change that application gateway and the end node, because you can tunnel across the V4 private network to that application gateway, and then it can do whatever it's going to do and come out on the other side of either V4 or V6, whatever happens. So yeah, there are multiple sides to this, and depending on where you are, we got complaints. I was the chair of the V6 transition tools, NG Trans in the IETF, and we got a lot of complaints that we had too many tools. Well, it's because there are scenarios like this, so there's a tool to solve that scenario, but there's 42 tools. Which one applies to you? Right? I'm trying to bucket them and say there's really 3 classes of tools, and if you stay within the first 2 classes, you're much better off. If you end up in the 3rd class where you've got these application gateways or header translators, we've got bumps in the API, we've got all kinds of choices for translation. If you end up in that space, it's because you have a unique need and you need to do that, and it's okay. We've got the tool, but you shouldn't go there unless you have to. And we should have made the rest of this simple enough. Magic picture basically just says, V6 is going to be everywhere, in particular in Asia, real soon now. It's already being deployed over cable into the homes, over Gigi into homes. So, it's there, it's coming to a neighborhood near you. One of the things I was trying to do with NG Trans was to divide the space. So we've got service provider class networks, which have a particular characteristic, enterprises and unmanaged networks, and they share some, depending on which way you draw this, unmanaged networks have some characteristics of service provider or of enterprise, and enterprise also has some characteristics of service provider, so I couldn't draw it very easily. We'll spend a lot more time on this next time, but again, dual stack is the primary tool. If a node can't be reached over V6, it can continue to use V4. Right? The only caveat is it's just like V4 today. So if the application doesn't work through NAT, it's not going to work any better. Right? Tunneling can be between the end systems. It can be between the routers. It can be between the end system and the router. There's all kinds of choices there, and there's also different mechanisms based on whether you're doing this between sites or within a site. Translation exists. We can do it in application gateways. You can do it in routers. NATPT is very similar to what you're used to in V4 NAT, but instead of just changing addresses, it also changes protocol types. Right? So, you're changing IP header on the fly and just rewrapping it and going. Has all the same scaling properties as a NAT. Right, so you definitely don't want to go here unless you really need to. One of the things, if we've got all of this wonderful stuff going and the service provider wants to provide a site with V6 service but doesn't want to mess with the core of the network, how are you going to actually route that stuff? Right, so we've got a BGP tunneling mechanism So you can move the BGP information for v6 between the edges that need to know it without having to corrupt the core infrastructure, right? So there's lots and lots of pieces, and you can glue them all together in various ways to come up with a network that does what you want to do. Just in case that's not complicated enough, if you've got an MPLS network, you can use the v4 MPLS infrastructure to move the labels around and do v6 over MPLS directly, right? So, this starts to look more like a native v6 service, but you're not using v6 and not touching your MPLS core. You're just adding v6 around the edges as you need it. So, with that, I've probably killed all the time, and then some. Any questions? Yes?
Do you have any information on the current status of just the current status of dynamic DNS, where that's at, dynamic updating to DNS? Because I understand that's going to be a pretty big...
Yeah, Paul Vixie was just outside the door right before we started, and I wish he'd stepped in here. There are people here that can answer that question, but I can't. So
I'll track Paul down.
Yeah, there are 2 or 3 other people here that would probably be able to answer the question as well, but, I'm sorry, I'd like to know. In the abstract sense, I don't know. In the case of, the Microsoft thing, since I happen to have come from there at one point in my life, that is definitely on the drawing boards. And in fact, the Microsoft IT guys are a little annoyed because when I was a program manager for v6 in Windows, I didn't give them a knob. So since they're a homogeneous shop, all nodes come up and register in DNS because that's part of what they do, right? And it's a nice, ubiquitous, Active Directory thing. You just register yourself. Well, with sending rules, as soon as I see that the other end does v6, I'm doing v6, right? So their traffic goes from v4 to v6, right? Whether they move the routers or not, it'll tunnel. Right? So they're a homogeneous shop. They've got this problem. The rest of the world has a little bit more graceful, migration. As you manage DNS, you manage that rollout. But yes, do we have the other mic? Turn off the mute.
I was trying to think of how many times during the day I actually type in, I was going to say an IP address, but an IPv4 address. Do you just do a lot more cutting and pasting in your world, or what's the reality of working with this? And you're trying to debug stuff over the phone.
Host.txt is your friend. Actually, until DNS gets up to date, most of what I do with v6 is in host.txt files, right? Because that's the only reasonable way. Yeah, I would be doing cutting and pasting. That's the argument that I use for why PlayStation is going to be fine, right? Because the guys who do peer-to-peer games on PlayStations, they've already got instant messenger windows open to each other, cut and paste, they're done. They don't need DNS.
So
right?
what's the show IP route look like with those kinds of access?
See if mine comes, no, mine's not back yet. Oh, yes, it did come back.
I think that's a real hurdle.
It's not. No, I mean the education is the hurdle, right? And so once you've gotten used to it, then it's not as big a deal. I knew I'd wake up sooner or later. So I can't make that any bigger, but that's just showing you some of the, the Windows version of ifconfig here. So that's a v6 address on this node right now on the wireless network. Right? That happens to be the privacy-based one. So that's the random number that it generated for the low order 64 bits. The one right below that is based on the MAC address of the NIC. Right? So the top one that I highlighted is the one that we use for any outbound connections, and the bottom one is the one that would register with DNS if there happened to be a Active Directory server here to register with. Yes.
What is the percent notation?
Percent notation is the scope. In particular, if you've got a node with multiple links on it, and you've got link scope addresses, you have to know which link it goes out. So, this is telling you that happens to be interface 14. So, you can keep track of which interface it actually is supposed to go out on. The ones down here further, with the %2s on them, those are the tunnel interfaces. Since they're auto-configured, those, they come up first, and that's why they've got low numbers. Alexander, yes?
Routing compared to IPv4 is similar, but if you introduce the site local, from your opinion, how does the site local supposed to be reflected into the current routing scheme?
Routing is the easy part, so actually I'm glad you asked it that way. I was afraid you were going to go somewhere else, and I'll go there anyway. Site local in routing is just another prefix, right? As far as all of the routers within the site, it's just another prefix.
How do you define the site? What is the site?
The site, okay, I understand. What is a site? And the question is, where do you administratively want to draw the boundary? If you're running 1918 addresses today, where do you stop using those and start using global public addresses? You've done that at an administrative boundary for some reason. It's the same decision that goes into this. I can't tell you it's the same place, but it's the same decision process. I may, choose to have all of a campus be one site as opposed to a building. Or I may choose to have my entire company be a site. It really depends on how big it is. For Cisco, a single site for the entire company doesn't make any sense. But say San Jose and everything on the West Coast probably does. And then everything on the East Coast has another site. Everything in Europe is another site. This is first order cuts, right? And then we can finesse it from there. But it's really site boundary is the administrative decision of where you're going to propagate that route. The distinction is your neighbors are not going to listen.
So you can do this today, right? With the IPv4, you don't need the site local address to do that.
Right. You can artificially
private based address or whatever the policy defines on the BGP doesn't propagate those addresses onto the global internet. You can do the same thing, right?
Right.
So there's something special about the local.
The thing that's special about it is we've architecturally defined it so everybody knows there is a space they can use for this, right? And they don't have to go carving up and have, if you used your existing public space but you only advertise part of it, somebody might misconfigure and announce out things you didn't want announced out, right? And your neighbor might listen because they don't know not to. With the site local prefix, we're saying, your neighbor shouldn't be sending you these. You should just hard filter them at the border. Now, whether you choose to subdivide that or not, that's an administrative function locally. So defining the edge of a site is really a local decision. But what we're saying is if you know it's not yours, you shouldn't hear it. You should have a hard filter on any inbound announcements of the site local prefix.
If you define a router that belongs to one site, then the problem is very easy, right?
Yes.
But if you attach to multiple sites, then it's a very complicated issue, right?
Yes, it's
left to the right.
Then you start getting back into the interface that it came in on, and which interface, because an interface can only be in one site. A router may be in multiple sites, but an interface can only be in one. So then you have to be much more granular about keeping track of which interface things came in on, and not just the fact you've got it in a table somewhere. So where I thought you were going to go was, how does this play with DNS? Right? And in fact, multi-faced DNS is going to have to become the norm if site local is used. Right? You've got two-face at least for site local and global, but you may want to even consider adding link scope addresses in there. That's why I say multi-face, right? You may have or multiple sites or, so there's a variety of things. So DNS may have some evolution to go through. In the current implementations, you're going to be somewhat restricted into what you can do with your site local addresses, just because DNS is going to restrict you.
Well, that depends on how you do naming, too.
One of the things that I found is that people think that names refer to boxes in DNS.
Right. No,
And that's a fundamental problem. If you think that a name refers to a box, then you've got a real problem in this situation. If you understand that the name refers to a network service access point, then it's much simpler to handle, and you just give a different access point a different name. You may have to cheat by using the box and a suffix or something to sort of work the transition.
You can manage it through names. You can also manage it through clever address selection rules, right? But there's definitely some work there. You had asked about routing before, and all I showed you was the interface configuration. It occurred to me that was all I did. So this is, netstat and things that are actually bound, right? So there's some v4 stuff bound, and then we get down here a ways, and then there's a little bit of v6 bound. It's because I don't have too many v6 applications enabled right now, right? So you get this colon designation for the what would have been 00 before.
So are there any good zero addresses left that have a lot of zeros left in them?
Get to Aaron quickly. Put in, vanity request now. Not only do I want an allocation, I want an allocation with a lot of zeros. So, any other